now that we're done with our warm-up and we feel comfortable with the parent functions, let's get back to our goal. We want to be able to transform those parent functions using this kind of complicated equation. And we're going to step through this one step at a time. So let's look first at a simpler version of this, which is just y equals f of x plus k, where f of x is a parent function that we know. For instance, maybe f of x is absolute value of x. So what does adding a number on to the end do? Well, this is a formula for what the y values will be at each x. And f of x is already telling you what the y values are. When you add on a y value and you add on a number to that same, to the function, you're adding on the same number to each y value you would have had. And the effect it has is to vertically translate or shift up by k units. So, for example, if we want to graph y equals x squared plus 3, we're going to lean heavily on our parent function. We know from our warm-up that y equals x squared makes a parabola and its key point is at 0, 0. For today, we're just going to be comfortable saying that we know there would normally be a key point at 0, 0. The question is, what is this going to do? And it is a vertical shift or translation, we can say it either way, up by 3 units. So instead of we're going to take our key point, which was at 0, 0 in the parent function, and we're going to shift it up by 3 units, sorry. And because this is where the vertex of the new parabola was going to be, I can just make my parabola from there. If I want to be like super good about this, I could actually like square the numbers. So this would be 0 squared is 0. I could go over by 1 and say 1 squared would be 1. 2 squared would be 4, and get my points that way. Negative 1 squared is 1. Negative 2 squared is 4. But for today, we're going to be pretty comfortable just going with the general shape. The same idea here. We want to know, what is the effect of this minus 1 going to be? Well, because it's a minus 1, it's going to be a vertical shift or translation down by 1 unit. So let's think of our parent function. Our cube root parent function looks like this. We should be familiar with it. Our key point is at 0, 0. And that point will shift down by 1. Instead of being at 0, 0, it will be at 0, negative 1. From there, we can still graph this concave down shape here and concave up shape here. It's got that inflection point. And here's our cube root graph. Okay. Again, if we wanted to be really fancy, we could do cube root of 1 is 1. The cube root of 8 would be 2 to get exact points. All right, why don't you try this on your own? And what you're going to do with these to get graded is at the very end of this PlayPosit, you're going to take a picture of all of the graphs you've done in this try section, and you're going to upload it, and it's going to be worth a lot of points. So I want you to graph f of x equals x absolute value of x minus 4. And all you really need is you can just draw an axis like this. You need to make sure it's clear exactly where the vertex is, and graph the rest from there. So go ahead and do that. And you should have put, either some tick marks like this to go down to negative 4. Put your vertex at negative 4, 0, negative 4, and made a V shape here because the absolute value parent function is translated down by 4. Another way you could have done this that would have been completely appropriate and gotten you full credit is to just put negative 4 like this and not show all the ticks. And that's good enough because it's now clear that your vertex is at 0, negative 4. So these are 2 options you have in doing this. All right, hopefully you were able to graph this. This is the linear parent function shifted up by 2. And so, instead of the y-intercept being at 0, 0, the y-intercept is at 0, 2, and it makes our linear shape. Should have a slope of 1, shifted up by 2. We can see that key point got shifted up by 2. All right, let's get a little bit, let's try this in a different way and see how you do with it. I want you to say, what is the equation that this function f of x represents? And because it's f of x, you should start with f of x equals and say what the equation is, okay? Hopefully you got it right, and you got absolute value of x plus 2. Notice that this is correct, but if you did this, this would be incorrect. The vertical shift has to come after the f of x. So you cannot have the plus 2 inside of the absolute value. It has to come after the absolute value for this to be correct. Okay, so that is a shift up by 2 from the absolute value parent function. Hopefully you got this one. This one is the, again, it's g of x. So your equation that you should have written down is g of x equals, you should recognize this as the square root parent function. It's the square root of x. But the critical point, the key point, is at 0, -2 instead of 0, 0. So it got shifted down by 2. This last one is a linear function, and it's h of x. So hopefully your equation was h of x equals x minus 2. All right, let's get a little bit more complicated. What if we have y equals f of x minus h? Now, there's something inside of the parent function that's getting changed. In this case, h is going to be a horizontal translation by h units. But there's something weird that's going to go on here. Absolute value of x minus 2, because that minus 2 is inside of the absolute value instead of outside, it's going to be a shift left or right. And a lot of kids suspect that it's going to go to the left by 2, to like x equals -2, and that's where the key point will be. But it actually goes, it shifts to the right by 2. And the vertex, instead of being at 0, 0, is at 2, 0. And let's look at y, because it's a little bit weird. The vertex of absolute value of x normally occurs at 0, 0, right? When x equals 0, when you do the absolute value of 0, that's where the vertex happens, because to the left, you're doing the absolute value of a negative, and it goes up, and the absolute value of a positive to the right, and it also goes up. And so the vertex occurs when you're doing the absolute value of 0. Well, think about what x value will make you do the absolute value of 0 here. You'll be doing the absolute value of 0 when x equals 2. And that's because when x equals 2, you'll be doing the absolute value of, when x is 2, 2 minus 2. And 2 minus 2 is 0, so you'll be doing the absolute value of 0, which is where the vertex will occur. So x needs to be 2 to get you to where that function normally has the absolute value of 0. For all horizontal translations, it will be backwards from what you might think it would be. For instance, the inflection point of x plus 3 cubed, instead of being at 0, 0, is going to occur at -3, 0. And this happens because when x is -3, -3 plus 3 cubed will give us 0 cubed. And that's what was happening. That's where the inflection point was happening in the original one anyway. So this is a shift left by 3. So whenever we have a function, in this case a cubic function, and you are adding or subtracting something inside of it, it will create a horizontal translation or shift, but it will be backwards from what the numbers appear to be. So let's see you try this on your own. Try to graph y equals square root of x minus 3 and do this on your sheet. You should have just a separate sheet of paper where you're keeping all of your graphs that you're making, so you can take one photograph of it at the end. So graph y equals square root of x minus 3, and you should recognize, hopefully you got it right, you should recognize that the shift was 3 to the right. And so instead of having the square root parent function with a vertex at 0, 0, that point will shift 1, 2, 3 to the right, and we'll make a square root graph from there. And that's going to be good enough. So it looks like this. It's this increasing but concave down shape from there. And we're also supposed to graph y equals square root of x minus 3 on the same graph. This is different. Notice this one is inside of the square root, and this one is outside. So go ahead and graph y equals square root of x minus 3. And hopefully you recognize that this is a shift down by 3 units because it's on the outside. That's back to our previous formula where we have f of x plus k, and that's on the outside of the function. That's a vertical shift. So in this case, it's a shift down by 3. and looks like this. So those are our square root graphs translated 3 to the right and 3 down. Let's see how you do on saying what the equations are of different functions that have these shifts. Here is, we're going to do one. This one I think is tricky. You should recognize what type of parent function this is. What type of parent function is this? And so you should know that for exponential parent functions, the critical point, the key point is not at 0, 0. Instead, it's at 0, 1. This is the tricky one. And so the point at 0, 1 got shifted. One way to tell is that the point 0, 1 is always 1 above the asymptote. We can see that the asymptote is still at y equals 0, and so the point that is 1 above the asymptote is right here. This is our key point because it's 1 above the asymptote. And so this point got shifted from 0, 1, it got shifted 1, 2, 3 to the left. So the question is, what exponential is it? And because the y value was 1 and then the y value was 2, 1 times 2 equals 2. There's a constant multiplier of 2 here. I saw that by looking at the two y values and seeing what they got multiplied by. So I can tell that this equation is g of x equals 2 to the x plus 3. And the reason I know this is because the point that would normally be at 0, 1 was shifted to the left by 3, and the constant multiplier was 2. And so it's y equals 2 to the x plus 3. We don't have to put parentheses here, although you could, because it's clear everything is in the exponent. Compare that to something like 2 to the x plus 3. This would be on the outside of the function. You do 2 to the x, and then you add 3. Here you're doing 2 to the x plus 3 power. So these are not the same. All right, try this one on your own. What is the equation of this? Think about what the parent function is, and think about what the translations are. And hopefully you got it correct. This is f of x equals x minus 3 squared. We know it's x squared because it makes a parabola, and it got translated 1, 2, 3 to the right because the parabola normally has a vertex at 0, 0. It was translated 3 to the right, and so we needed to put that inside of the parentheses. Something like x squared minus 3 would shift it down. All right. Let's see how you do on h of x. What is the equation of h of x? And it should start with h of x equals. So h of x equals. We see that this is an absolute value parent function. And so it is the absolute value of, it got shifted 1 to the left. So that goes inside of the absolute value. And 1 to the left, it's backwards from what you might think, is x plus 1. This is a horizontal shift left by 1. Let's see how you did on c of x. C of x equals. This is a cube root parent function. We should recognize it as the cube root parent function. And we're looking for the inflection point. The inflection point happens right here. And so that is 1, 2, 3, 4 to the right from 0, 0, which is where it normally is in the parent function. And so we know it's the cube root of, to make it go 4 to the right, we need x minus 4. Hopefully you feel good about that. All right, these last two, try them on your own. F of x equals, let's see how you did. F of x equals, this is a shift to the left. This is x plus 3 squared. That's how you make it shift to the left. G of x equals, let's see how you did on coming up with the equation here. This is a shift up by 3, and so this is x squared plus 3. Notice that they both have a plus 3 in them, but when it's on the outside of the parentheses, it shifts up by 1, it shifts up or down. When it's on the inside, it's a horizontal shift left or right. And that's the major difference between our two equations, where we had first f of x plus k, and second f of x minus h. So if it's inside the parentheses, it's a horizontal shift. Outside the parentheses is a vertical shift. All right, let's get a little trickier. We're now going to put them together. F of x minus h plus k. Well, we should be able to predict what's happening here. This will be a vertical translation up by how many units? Well, k units, because the adding on to the outside is what makes a vertical translation. It's a horizontal translation, or shift, by how many units? Well, h units. And remember, we use x minus h here because this one is backwards from what you would think it would be. Okay? So with that in mind, we want to graph f of x equals x plus 3 squared minus 1. This is going to have a horizontal translation of how many units? Good. It's a horizontal translation of -3 units. It's 3 to the left because it's backwards because it's on the inside. And it's going to have a vertical translation of how many units? Good. It's -1 units. So it's going to be 1 down. And so when we graph it, this is the quadratic parent function. It's going to make a parabola. Instead of having a vertex at 0, 0, we're going to count 1, 2, 3 to the left and 1 down. And the vertex is going to be at -3, -1. So 3 to the left and 1 down. And from there, it makes a parabola. Hopefully we feel okay about that translation. Let's do one more example together. This is going to be have a horizontal translation of how many units? It's going to be 1 to the right. And we can tell that because of the x minus 1 in the exponent. And it's going to have a vertical translation of how many units? 2 units up because of the +2 on the outside. Now, these are a little bit trickier. And in exponential equations, what we're going to do is we're going to start by doing the vertical shift up, because that will change the asymptote. Instead of having an asymptote at y equals 0, the asymptote is also going to shift up by 2 units. It shifts to the right by 1, but it's an infinite line, and so shifting to the right by 1 doesn't do anything. And then we're going to take our key point. Remember, it's not at 0, 0. The key point for exponentials is at 0, 1. So we really want to be familiar with those parent functions. And looking back at our exponential, we've got this key point at 0, 1. There was no point at 0, 0. And so we're going to take that point and shift it 1 to the right and 1 to the right and 2 up. It will always be 1 above the asymptote. And then we can just draw it in. We can follow the asymptote and go up from there. And so this is what our exponential looks like that got shifted right by 1 and up by 2. So that's a little tricky. All right, let's see you try one on your own. The vertex here will be at what point? The vertex will be at -3, 1, because the vertex of the parent function is at 0, 0. It got shifted 3 to the left and 1 up. Go ahead and put your graph in your separate page that you're going to take a picture of at the end with all your graphs. You need to graph this on your own. And hopefully you put the vertex at -3, 1, and because it's absolute value, you made a V shape going up from there. It's got those 2 constant rates of change. All right, this is a cubic function. It doesn't have a vertex. Instead, what's the key point called? It's called an inflection point. And the inflection point is going to be at, let's see, this is 2 to the right and 1 down. So the inflection point is going to be -1. So 2 to the right and 1 down. And the inflection point of the parent function is normally at 0, 0. So hopefully you're able to graph this. Go ahead and graph it on your own in your paper. And let's see how you did. The inflection point is at 2, -1, and it makes this cube root parent function. Oh, sorry, cubic parent function. Boy, not cube root. This is a cube root. This is wrong. It is a cubic parent function, which looks like this instead. So instead of being more horizontal, it's more vertical. It still has an inflection point, but the shape is very different. So hopefully you got this cubic parent function and you didn't do a cube root like I started to do. Okay, let's see how you do on identifying graphs. So we have F, G, H, and L here. Let's start with f of x. What is the equation for f of x? You want to be able to identify what the parent function is of f of x, and then how it got shifted. So let's see, hopefully you got that this is a cubic parent function because it makes this shape that you should recognize as a cubic shape. And the inflection point is right here. It's 1, 2, 3 to the left and 1 up. So this needed to be f of x equals x plus 3 to make it go 3 to the left, cubed plus 1. Okay. Let's do g of x next. G of x is going to equal, this is an absolute value parent function. So hopefully you got the equation right here. What is this equation? Well, it got shifted 1, 2, 3 to the right, 1, 2 up. So it's absolute value of x minus 3 plus 2. This is 3 to the right and 2 up, which is how we got our key point, the vertex, to move over by 3 and up by 2. Let's look at h of x next. What is the equation of h of x? Hopefully you're able to get this correct and notice that it's a square root parent function because it's got this part where it doesn't keep going to the left because they're undefined values. It's got a vertex here, and that vertex was shifted 2 to the left and 2 down, and so it's square root of x plus 2, that does 2 to the left and 2 down. Our last equation is L, and hopefully you were able to go ahead and write down the equation right now. This is L of x is equal to, I see this point was shifted 1, 2, 3 to the right and 2 down. So this is x minus 3 minus 2. And this is a linear function. This is a completely acceptable way to write it, but you might have also noticed that it goes through the point 0, negative 5. Well, because this is linear, these parentheses aren't actually doing anything. This is the same as x minus 3 minus 2. And these are like terms. This is the same as L of x equals x minus 5. In fact, you can pick any point. Like, this is another point. In linear functions, there isn't one key point. Any of the points could be key points. So for instance, you could think of this as a shift to the right by 5. So L of x equals x minus 5. That's a shift to the right by 5, but these parentheses aren't doing anything, and so it's the same as both of these. All of these equations are fine for linear functions. It doesn't really matter which point you look at as the key point. Okay, let's see how you do on this one. So write the equation for this one. You should recognize it as a cubic function. This is cube root function, sorry. This is the cube root of. Its inflection point is 1 to the right and 1, 2, 3 up. So to make it go 1 to the right, we do x minus 1 inside the cube root. And to make it move shift 3 up, we need a plus 3. All right, let's see how you do on this trickier one. This is a function, and notice that this point is 1 above the asymptote, and this point is 3 above the asymptote when we move over by 1. So hopefully you can do this. If you missed this, I'm not going to take off points, but it's a good thing to try. It's a nice advanced problem. So y equals, we should recognize it's exponential. It's got this asymptote. And the question is, what's the constant multiplier? Well, 0, 1 is this point. The next point is 3 above, and so the constant multiplier is times 3. So you look at how many above the asymptote the first point is, and then how many above the asymptote the next point is, and that's the constant multiplier. So in this case, the constant multiplier is 3, and so it's going to be 3 to the x. The point that is 1 above the asymptote is where 0, 1 was translated to. So 0, 1 is the key point on exponential parent functions. Remember, that's the weird one. So 0, 1 is the key point. It's always 1 above the asymptote. And so that point got shifted 1, 2, 3, 4, 5 to the right and 1 up. So minus 5 and plus 1. Well, notice that plus 1 moved the asymptote up by 1 as well. So you can look at where the asymptote is to get where the plus 1 is, but you still have to find out what point is 1 above the asymptote to see how many it shifted over from 1, 0. So that's a tricky one, and I will tell you we'll work more on those later this year. If you're still having some trouble with exponential functions right now, that's completely understandable. All right, let's move on to our fourth set, which is what happens if we put a negative in front of a parent function? So a negative in front of the absolute value of x, or a negative in front of 3 to the x. Well, what this negative does is it takes all of the y values that you would have had and makes them negative. So any y values that would have been positive become negative. Any y values that would have been negative, the negative of a negative will be a positive, And so what this does is it takes all the points that are above the x-axis and moves them below the x-axis, all the points that were below the x-axis and moves them above the x-axis, and this is a reflection across the x-axis. And so let's look at how this looks for our parent function, y equals negative absolute value of x. Any point that is at 0, negative of 0 is still at 0, so it doesn't change where the vertex is. But the point at 1, 1 is going to now be at 1, negative 1, because all the y values got made negative. The point at 2, 2 is now going to be at 2, negative 2, because all the y values become negative. Negative 1, 1 is what we would have normally had on the parent function, and that will become negative. And we can see that the absolute value parent function, that v, got reflected across the x-axis. The same thing will happen for this exponential. There's normally an asymptote at y equals 0, and that won't change because the negative of 0 is still 0. There's normally our important key point is at 0, 1, and that's going to become negative. It'll be at 0, negative 1. Our next point would normally be 3 to the 1, which is 3, but that is going to reflect and become negative 3. Normally, they'll be heading towards the asymptote above the x-axis, but now it'll be heading towards the asymptote below the x-axis. And so we can see that this exponential function gets reflected across the x-axis. So instead of our parent function that we're used to from our warm-up, it gets reflected across the x-axis. All of those positive values become negative y values. Okay, and so let's see how you can do on saying what the equation of these are. What is the equation of f of x? Well, f of x equals, this is a quadratic, it makes a parabola, but it's got reflected. Instead of opening up, it's opening down. So this is negative x squared. We notice the vertex is still at 0, 0. It didn't get shifted in any way, so we don't need to add or subtract anything. What is the equation of g of x? Well, this may look to you a lot like a cube root function, and it is a cube root function, but you'll notice cube root of 1 is normally positive 1. But now when we do x is 1, the y value is negative. You should notice that this got reflected compared to the original, which would have been like this, right? And so this is g of x equals negative cube root of x. And lastly, you have this one, and this is h of x. Go ahead and write the equation. Hopefully you were able to get it right, and you got h of x equals negative. This is going to be 2 to the x. And the reason I know it's 2 to the x is because the point that is 1 below the x-axis is our key point, and then it got multiplied by 2 going over to the next one. So 1 times 2 got me 2 below. So it went from being 1 below to 2 below the asymptote, and it got multiplied by 2. But it got reflected across the x-axis, and that's why it's not an exponential going up like this. All right, let's put this all together. Our last thing, and I know we're all getting tired because we made a ton of graphs here and we're almost done. Our last thing is putting it all together. If we have a number in front times f of x minus h plus k, if this number in front is negative, it will reflect over the x-axis. If we have a number inside of the function, that will make a horizontal shift left or right. And if we have a number adding on or subtracting in front, that will be a vertical shift up or down. So let's look. What type of function do we have here? It's a linear function because there is no squaring or square root or anything that's going on here. And so we're going to do the linear parent function. This is a translation up by 3. This is a translation left by 2. And this is a reflection across the x-axis. So let's look at how we do this. I'm going to take the key point of the parent function, which is 0, 0, and shift it 2 to the left and 3 up. And a reflection means that instead of increasing, the function is going to be decreasing now and have a slope of negative 1. So that's what a reflection ends up looking like. It has a slope like this. These points are not in exactly the right place. I didn't do a great job of graphing the rest of this line, so don't pay too much attention to the rest of this line, but this key point is in the right spot. So negative 2, 3. Okay. All right, what type of function do we have here? It's a quadratic because of the x squared. And where is the vertex going to be? Well, the vertex is going to be at 1, 2, 3, 4. The vertex is at 3, 4, because this is a shift to the right by 3 and up by 4. But we have this negative sign on the outside, and so it's going to reflect. And so instead of being opening up, this parabola is going to open downwards. It'll be a concave down parabola. All right, let's see how you do on these last few problems here. We have f. Go ahead and write the equation for f of x. We should recognize this is a cubic, and the question is, this is x. You got, which one is the key point? Well, you have to find the inflection point. That's where it switches from being concave down to concave up. It got shifted 1, 2, 3 to the left and 2 up. So 3 to the left is plus 3, backwards from what you might think. And this is a cubic function, so it's cubed. It shifted 2 up, so we need a plus 2. And the question is, did it get reflected? And the answer is no. The cubic parent function already has this shape. This one still does. There is no negative in front. And so it's just f of x equals x plus 3 cubed plus 2. Let's do k next. K of x equals, go ahead and try that on your own. And so we should notice that this is a square root function. Here's my key point. It got shifted 1, 2 to the left and 1, 2, 3 down. So it's square root of, to make it shift 2 to the left, I need x plus 2 inside of the square root. That's 2 to the left. 3 down is a minus 3 on the outside. And the question is this the normal parent function or did it get reflected? Well, the normal parent function of a square root is opening, has this shape where it's increasing and concave down. This one is decreasing. It got reflected across the x-axis. And so this one does need a negative sign in front. So we have to be a little careful about that. All right, let's look at g. G of x, we should notice, I'll put this a little bit lower. G of x, we should notice it's a quadratic. So the key point is the vertex. That vertex was shifted 1, 2, 3, 4 to the right and 1, 2 up. To shift it 4 to the right, we need x minus 4 squared. To shift it 2 up, we need the plus 2 there. And the question is there a negative on the outside? And the answer is no, there is not, because it's opening up still. It didn't get reflected. If we had had a negative here, if this had gone there, the parabola would open down instead of up. Okay, our last one, h of x. Go ahead and write the equation of h of x yourself. H of x is an absolute value function. The vertex is shifted 1, 2 to the right and 1 up. So x minus 2, that shifts 2 to the right and 1 up. And the question is, do we need a negative here in front? And the answer is yes, we do. We need a negative in front, and that's because it is opening down instead of up. And so the parent function, which normally opens up, got reflected across the x-axis. Okay, hopefully you're feeling pretty good about this. Let's add one more graph to your page of graphs that you're doing by yourself. So graph on your own. Negative cube root of x plus 5 minus 2. Take a minute to do that. And hopefully you took the inflection point, which would normally be at 0, 0, and shifted it 5 to the left, backwards, and 2 down. And normally the cube root parent function looks like this, but that negative in front is going to reflect it. So these are going to go down and like this. So it should look like this. This is our, oh man, you guys couldn't see that. Oh no, I hope this wasn't all off the screen. This is 5 to the left. The inflection point is 5 to the left and 2 down. And the negative makes it, instead of looking like the normal cube root parent function, it goes down to the right and up to the left. And so there is your graph. Go ahead and take a picture of all the graphs you made today and submit that now. Let's see how you did on those. And last but not least, I want to show you something that throws some kids off, but is pretty easy. Let's look at y equals 3 plus square root of x minus 4. This looks a little bit different because the 3 is in front, but you can switch the order of this. This is the same thing as square root of x minus 4 plus 3. So if there's ever just a constant in front that's adding, we can move it. If it looked like this, 2 minus square root of x plus 5. This is not the same as square root of x minus 5. This is not square root of x plus 5 minus 2. This is wrong. This is the same as negative square root of x plus 5 plus 2. So the 2 can be moved to the back, but that negative is still we still need the square root to be negative. Okay, so be careful on that. So that's it for today. Hopefully you feel good about transformations. This was a fairly long lesson, and it's one that we're going to be using throughout the year. It's a pretty important lesson. So if you have any questions on your homework, feel free to ask them, and we'll get a chance to check your knowledge in just a second.